Okay, so let's do another polynomial division problem. This one may be even trickier because we're dividing a cubic by a quadratic, and it's a quadratic which is not going to be a factor, a clean factor of this cubic. So we can have a remainder which could potentially be a linear term, which people generally don't expect. You get so used to dividing by linear terms, and it's a real number for the remainder, that these ones can throw you off a little bit. How do I know, by the way, that this is not going to be a factor? Well, it's a factor of this thing if and only if they have roots in common, right? If this is a factor of it, after you factor that, all of its factors are factors of this. So according to the factor theorem, that means that all of its roots are roots of this. And this would be if it has rational roots. I'm assuming these things have rational roots, by the way, or else we couldn't do this. It's very difficult to do it, of course, with irrational roots. But how do I know that the rational roots of this are not the rational roots of that? Well, the rational roots of this have to be factors of 5, right? They have to be plus minus 1 plus minus 5 according to the rational roots theorem. Factors of this, or rational roots of this, have to be plus minus factors of 9 over plus minus factors of 2. So plus minus 1 plus minus 3 plus minus 9 plus minus 1 over 2 plus minus 3 over 2 plus minus 9 over 2. Tongue twisters for the roots. So this one is going to have a remainder, and we can see how to do that, which is why I picked this one to do specifically, because I don't think we've done one of those yet. So we do the same thing that we always do, right? This is 2x cubed minus 7x squared plus 17x plus 9. And we're setting it equal to x squared plus 2x. Maybe a more recognizable 2 there would be a good idea. X squared plus 2x plus 5. And then we're multiplying this. We're multiplying this by the quotient, which is a function of x that's going to be a linear term, and then plus the remainder, which I'm going to write as r of x to indicate that it can be a linear term, so it can have an x in it, right? Technically, when it's a constant, that still can be thought of as a function of x. It's just a constant function of x, but it doesn't have any x's in it. So we just write it as r because it's in the real numbers. But with this one, it could definitely have an x in it. So let's do our usual process. We have a 2x, and this is another complication, right? We have non-one leading term, which again can throw us off if we haven't seen this kind of thing before. So it is 2x cubed that we want from the first term here, right? We have an x squared to multiply by, so this is going to be 2x, right? We need a 2x to multiply by the x squared to get 2x cubed. And it gives us a 2x cubed, which is perfect, right? This is perfect. We have a 2x cubed here. And then it multiplies by the 2x and gives us, I think that's going to be 4x squared. That's going to be 4x squared here. And we're looking for a 7x squared, so we're going to have to do something about that. But then we also can't forget to multiply it by the 5 here. And this is the main sort of complication when you're dividing by a term which is, so a divisor term, which is higher degree than 1, right? It's like a squared term here. We get this extra thing, and we need to know how to deal with this. So we multiply the 2x by the 5, and we get, I think this is going to be, maybe in the same color pen, this is going to be 10x. We get 10x here. Actually, I should probably put it in the same color though, 10x. And this is, so 2x times 5 is 10x. This is one of the steps that really sort of throws people off when we're dividing by, including me back in the day when I was learning this for the first time. This was so confusing. When you're doing the sort of algorithm where you just memorize the steps and then subtract and add things and push things around, it's very hard to sort of deal with curveballs like this, right? What is going on with this? We're used to just matching this term, but now we have this term throwing us off. If we understand the process, if we understand the idea behind it, then we can handle this, right? We know that we're just matching the next term, and then with each term that we put into the quotient, we're matching the next term of the dividend, and then whatever else comes out, and then we go to the next step and we aggregate it and see what is the total output at this point, and then use the next term to match the next power of x. If it's equal at the end, it's equal, that's great. If not, we add a remainder to make it equal, right? And so this, if we understand this process, we're going to be able to deal with this. So let's do that. We have, let's actually do the next step in this process. We have 2x cubed, which is the number that we need. We don't have the right number of x squareds, right? We want 7x squareds. We have 4x squareds. So what do we have to put here? The next thing is going to be whatever gives us, I think it's 3x squareds, right? We need another 3x squareds to make that 7x squared. And we need to add those 3x squareds to the 4x squared that we have, right? We have 4x squared, we need 7x squared. So we have to get another 3x squared from the next term we put in here. What do we multiply x squared by to get 3x squared? Well, I think that's 3. So we're going to put in the 3 to get this 3x squareds that we need. And that will work, right? We'll get the right number of x squareds. We will have 7x squareds there. Then we will multiply the 3 by the 2x, and we will get another, not 2x, 6x's. 3 times 2 is 6 last time I checked. We will get 6x's, and then we'll multiply by the 5 and give us, I think this is 15, right? We're going to get 15 as the last term here. And then what do we do? Well, we're going to aggregate. This is like I said, right? We're going to add up all the stuff that we have. We have 2x cubed. That is the right number of x cubed. We have 2x cubed. We have 7x squareds, right? 4 plus 3 is 7x squareds. That is the right number. Then we have 10x plus 6x. So this is 16x. We have 16x's. How many x's do we want? We want 17. So this one is off. We have a 15 plus 15. How many? And that is the constant. What is the constant that we want? We want it to be 9. So these two are good. These ones need some work, right? These are not correct. What this is saying, by the way, is that so far, the result of multiplying the divisor, which we were given, by the quotient, which we have been constructing here, the result of this so far is 2x cubed plus 7x squared plus 16x plus 15. That's what we get if we multiply these things out. That's not what we want it to be, though, right? We want it to be equal to this. We want it to be equal to 2x cubed plus 7x squared plus 17x plus 9. We have the first two right, and the last two are off. So what do we do? This is where the remainder comes in, right? This thing is not a factor, right? This x squared plus 2x plus 5 is not a clean factor of this, so we're going to have a remainder. We're going to have to add a remainder to make them equal. What is the remainder going to be? Well, I just look at the 17x, and I think, what do I have to add to 16x to make it 17x? Well, we have to add x, right? Plus 1x is going to make the 16x into 17x. How do I turn the 15 into a 9? We subtract 6. So we subtract 6 here. So our remainder, and this is the first linear remainder that I think we've seen, which is great because, again, this is an often sort of neglected one that people don't come across, and then you get it on a test. It's kind of a curveball. X squared plus 2x plus 5x times 2x plus 3, and then plus x minus 6 is equal to, well, 2x cubed plus 7x squared plus, we'll add the x to that 16x. Let's consolidate these ones, right? This is going to be plus 17x. And then the 15 minus 6, that's going to be 9. This is going to be 9. And this is exactly the dividend, right? This is the dividend. This is what we were trying to make it equal to. So this is our division statement, right? Actually, our division statement overall, we write it usually in the other way. Final division statement is 2x cubed plus 7x squared plus 17x plus 9 is equal to x squared plus 2x plus 5 times 2x plus 3 plus x minus 6. That is the remainder. And if we wanted to rewrite it, because sometimes, well, people prefer to write it in division form, usually in applications like finding slanted asymptotes, so finding oblique asymptotes, which we're not doing here. But if we were to do this, and again, just because some people want to see the division statement, we can divide everything by x squared plus 2x plus 5 and see that so that dividend divided by this divisor is going to be equal to 2x plus 3 plus x minus 6 over x squared plus 2x plus 5. And so this is actually saying, I know that we're not doing this here. This wasn't the I don't want people to feel kind of blindsided. It's not what we were doing with this problem. But if you remember when you were trying to find oblique asymptotes, right? They occurred exactly when you had a rational function, so a ratio of polynomials. The numerator was 1 degree higher than the denominator, and the denominator was not a factor of the numerator. So we actually have an oblique, and so what this says is if we take the limit, right, as x goes to plus minus infinity, as x goes to plus minus infinity of this expression, well, this thing is going to go to zero, right? The denominator grows much faster than the numerator. This grows quadratically. This grows linearly. We have videos where we go into this in detail, so don't worry about this if this seems a little bit weird. But what this is telling us is that we have an oblique asymptote at y is equal to 2x plus 3, an oblique asymptote. So if we're graphing this thing, right, what happens is we have the line y is equal to 2x plus 3, y is equal to 2x plus 3. And then the graph of this is going to do something like that. It's going to flatten out against that. I don't know what the rest of it is. We haven't analyzed this, but that's the idea, is that the end behavior of this will be an oblique asymptote. It will flatten out against that line, this non-vertical, non-horizontal line, 2x plus 3. And we call that a slanted asymptote or an oblique asymptote.